Hello everyone, welcome to lab number 5 of AWS Data Engineering. In this lab, we'll dive into processing logs using Amazon EMR. Now, in this lab, we will learn how to handle large datasets and perform data processing tasks efficiently. Let's get started. In this lab, we'll use Apache Hadoop, an open source framework for processing massive amount of data across a cluster of instances. Now, Hadoop can run on a single EC2 instance or scale up to thousands of instances. It uses Hadoop Distributed File System or HDFS to store data across multiple nodes. We'll also leverage Amazon S3 and Apache Hive for querying our data. In this lab, you will use Amazon EMR to process logs that are stored in an S3 bucket. To process the data in Amazon EMR, you will use Apache Hive. Hive is an open source data warehouse infrastructure framework that is built on top of Hadoop and is often used to process large datasets. With Hive, you can query large datasets with SQL-like queries. And when you run a Hive query, the request is translated into a yet another resource negotiator or YARN job. YARN is the part of the Hadoop software that coordinates job scheduling. By the end of this lab, you will be able to launch an EMR cluster through the AWS Management Console, run Hive interactively, use Hive commands to create tables from log data stored in Amazon S3, join tables and store the results back in Amazon S3, and query tables stored in Amazon S3 using the Hive. Before we proceed to our main task, there are some prerequisites that we need to do. So first go to S3 and create the S3 bucket that will contain our Hive output. So choose create the bucket and I will name this Hive-output any random string. It has to be unique. For myself, I will name it 2024-0708-1, which is of course when I've created it. Go with the default options and choose Create Bucket. We're done with the first prerequisite. Next, after we have confirmed that it has been created, we have to go to IAM and create the two roles that we will be using later. So go to Roles and create a role. For the service, we have to choose the EMR. We'll be doing this twice. Choose the first option, EMR, and you'll see a policy that's automatically attached. And for the role name, put in EMR underscore default role with the DNR being capitalized. Choose the other default options after reviewing and create the role. After this one, let's create another role, choose EMR, and instead of the default EMR, we'll choose EMR role for EC2. The permission is automatically attached when you've chosen the right service. Click Next, and for this one, name this as EMR underscore EC2 underscore default role. Save it and create the role. We're now done with the creation of our two IAM roles, which we will be attaching to our Apache Hive. Next up, we need to go to EC2 and create our key pair. On the upper right section, choose the key pairs under the Resources tab and create a key pair. Name it as VOC key, and we will be using this later in our CloudFormation template. Bear in mind it should be .pem and create a key pair. This will automatically download the key pair and keep it because we will be uploading it later in our Cloud9. Now we are at the last step of our prerequisites. We need to go to CloudFormation to create a template that will automatically create the other AWS resources for us. So choose Create Stack with new resources and upload the template file that will be found in the description of this video in the GitHub link. Choose the EMR lab.yaml and upload it, and choose Next. For the stack name, go with EMR lab. Review all the parameters. You'll see here the VOC key that we have done or created earlier. Review the other Default Options, and click on Submit. It will take some time for this to be fully created, but you can monitor the progress by going onto the Events tab and clicking on Refresh to see if any of the steps or resources failed to materialize. After the completion of the creation of resources, you'll see the status to be create_complete. And you can go to VPC and check that we have successfully created a virtual private lab. We've named it as Lab VPC, including the subnet, which is the lab subnet. For the root table, you see here the lab root table, and these are the resources that our cloud formation template have managed to create. We have now successfully completed our prerequisites and are now ready to proceed to our main tasks. Let's get started. In this task, you will launch an EMR cluster with Hive installed. To access the EMR in the search bar to the right of the services, search for and choose EMR. After that, launch the process to create an EMR cluster by choosing Create Cluster. In the name applications, set the name to Hive EMR. For Amazon EMR, choose the version of EMR-5.29.0. Uncheck everything except for Hadoop 2.8.5 and Hive 2.3.6. In the cluster configuration section, set the instance type and the number of nodes to choose. For the main node, choose M4.large from the list. In our particular case, we call it the primary node, but for other versions, it's called the main node. Choose the same instance size, M4.large, for the core node. We can remove the instance group of the task as it's just optional. Under the cluster scaling and provisioning, set the core instance size to 2. In the networking section, for network, choose the lab VPC, the one that we have created earlier, and for the subnet, it automatically chooses the lab subnet. For cluster termination and node replacement, deselect the Use Termination Protection option. So make sure it's not selected. Go with the default options, but for the cluster logs, choose the bucket that we have created specifically for this one for the Hive outputs. For the security configuration, for Amazon EC2 key pair for SSH to the cluster, choose the VOC key that we have already created. This is the VOC key that we have created earlier in the prerequisite section. For the service role, choose the EMR default role, and for the EC2 instance profile, choose the EMR_EC2_ default role. After a final review, choose to create the cluster. You have now been provisioned a cluster. While we are on the Cluster Summary tab, go to the Network and Security section below and expand the EC2 Security Group's firewall to see the security group for the main node. It may take a minute or two if you don't see the link yet, so just refresh the page. A new tab opens to the security group in the Amazon EC2 console. In the bottom pane, choose the Inbound Rules tab, then choose Edit the Inbound Rules. At the bottom of the page, choose Add Rule, and then configure SSH access for the AWS Cloud9. For the type, choose SSH, and for the source, choose anywhere-IPv4, and save the rules. Now, we have to wait to confirm that the cluster is now available. So let's go back to that tab, and you'll see the status and time. The status should show waiting, where waiting means it's waiting for us to give it command. It might take 10 minutes since you created the cluster for it to finish provisioning. So after that, we're done. In this task, you provisioned an EMR cluster with Hive running on it. You also configured the security group for the main node in the cluster so that it will accept secure shell connections or SSH connection. In this task, you will use an SSH client and an Amazon EC2 key pair private key to connect to the Amazon EMR main node. So we go to Cloud9 and open the environment that has been created for us using the CloudFormation template that we've had earlier. As always, this may take some time in order for the instance to start. While we're waiting for it to finish running, go to EMR again, and in this cluster management section of the summary tab, find the public DNS address for the main node. We have to copy this into our clipboard and paste it into the Cloud9 text editor, for we will be using this to connect to our Hive instance. Open a new file and paste the public DNS for the primary node we have copied earlier. Now remember the VOC key we have earlier downloaded? You will now upload this file as a local file into the Cloud9 IDE. So upload local file and drag and drop here the VOC key that was automatically downloaded when we have created the EC2 key pair. So to modify the permission, open a terminal. For that file, you can see that the VOC key.pem is already here in our environment. To modify the permission, we run the following code. Establish an SSH connection to the cluster's primary node by running the following code. Replace the public DNS address of the main node that you copied earlier. So it will be after Hadoop at and paste the public key. So since we have it in our text editor, I will just copy it from the text editor and paste it after the @ sign. When prompted to continue connecting, enter yes. And this message should indicate a successful connection. You are now connected to Amazon EMR primary node, which is running on an EC2 instance by using SSH from the AWS Cloud instance. So congratulations! In this task, you successfully connected to the primary node on the cluster by using the AWS Cloud9 terminal. In this task, you will configure a logging directory for Hive and then start an interactive Hive session on the EMR's cluster's primary node. So to create a logging directory for Hive, we run the following command on the terminal. Note that this code can be copied from the link in the GitHub available in the description of this video, but for now, we'll type this. So the Hive client expects this directory to exist when it's run. You will use the Hive client in a later step. Now let's configure Hive to retrieve the name of the S3 bucket where we want to store the Hive output. We run the following command. It's the same command that we've run every time we want to check our S3 bucket. So we see here the name of our Hive output bucket, and let's copy it again and paste in our text editor, for we will be using it in the next query. This video will now type in this query, but you can just copy this from the GitHub file where we are under task 3. Replace with the full name of the Hive output bucket that you have in your S3 for this to run. This command takes a few seconds to run and then displays the following output. Right there. That shows that we are now connected to the interactive Hive client. So excellent! In this task, we are done configuring logging for Hive and was able to establish a successful connection to the Hive. In this task, you will create 2 Hive tables that will form your data warehouse. The tables will reference the data that is stored in Amazon S3, and these tables will serve as the input data for queries that you will run later in the lab. Now, in this task, you will use HiveQL, an SQL-like language, to load the data and run queries. Now, to create an external table named Impressions, run the following code in the AWS Cloud9 terminal. Again, this is found in the GitHub file, HTML file that's available to you. Notice that this command created an external table. When you create an external table, the table data is not copied into HDFS. If it did not specify external, the table data would be copied into HDFS. To see how many partitions the impressions table currently has, run the following command. It's describe formatted impressions, being the name of the table. This output will describe the column names, location of the data, number of partitions, and other metadata about the table. Notice here that the number of partitions is 0. To inspect the input data and apply partitions to the metastore, we run the following command. It's the set hive.msck.path.validation equals ignore, and the msck repair table impressions. After the command finishes running, the output should be similar to the following, and we can run the describe formatted impressions command again to check that we now have 241 partitions that exist in the table. To discover its partition, we run the same command as the impression, which is msck space repair space table space clicks. This might take some time for this to run. In our case, it was 13.1 seconds. To verify that two tables now exist, we use the show tables command, and to describe the clicks table, we run describe formatted clicks command. Perfect! In this task, you successfully created two external Hive tables that can now be used to query data. In this section of the lab, you will join the impressions table with the clicks table. By combining information on the ads that were presented to a user, the impressions data with information on which ads resulted in the user choosing the ad, or the clicks data, you can gain insight into user behavior and target and monetize advertising services. So the following diagram illustrates what you will accomplish in this task. Both the clicks and impressions tables are partition tables. When the two are joined, the create table command will tell the new table to be partitioned. So to create a new external table named joined impressions, we copy the command in our GitHub file and run it here. Create external table, and we will name it joined impression. The joined impressions table defines the same 7 columns that exist in the impressions table. However, the new table also contains an 8 column named clicked. So unlike the first two tables that we have created, which already contain table data and the location specified, we defined a new location that does not yet have a data. Notice here the stored as sequence file clause compresses the data before it is stored. Using this native Hadoop format for compression will provide better performance than keeping the data in JSON format. So to create a new temporary table in HDFS named TMP impressions, copy the code corresponding to it in the GitHub file and run and create table TMP impressions. This table will store temporary data in the local HDFS partition. You know that it is stored in HDFS, not in S3, because the command did not specify external as the table type. The table has the same column names as the impressions table. To insert the impressions log data for the time duration reference, we run the following command: the insert override table TMP impressions. Now, this command runs a MapReduce job to process the request, and the output is similar to what you're seeing on the screen. The insert override table command will replace any existing data in the TMP impressions table with the new data. Now, the select command selects the data from the impressions table, but only selects the records that correspond to a specific period of time. Because impressions table is partitioned by request begin time, only the partitions that are relevant to the specified time duration are read, which improves the performance. Next, we will create a temporary table named TMP underscore clicks and insert data into the table. The same code is found in the GitHub file. To insert data into the TMP underscore clicks table, we run the code insert override table found in the GitHub file. The command launches another MapReduce job, and the output again is similar to what is shown in the video. This will take approximately 1 minute to complete. To create a left outer join of the TMP underscore clicks and TMP underscore impressions that writes the resulting data set to the joined underscore impressions table in your S3 output bucket, we run the following command that we have. It's the insert override table joined underscore impressions. Another MapReduce job runs, and this will take approximately 30 seconds. The left outer join returns all records from TMP underscore impressions, even if the join condition does not find and return matching records from the TMP underscore clicks table. If matching records are not found in the TMP underscore clicks, null values are returned for each column. The left outer join excludes any data from TMP underscore clicks that did not originate from an impression in the selected time period. Because the joint underscore impressions table is stored in Amazon S3, the output can be made available to other EMR clusters. Congratulations! In this task, you successfully combined the data from the two source tables into a single queryable table. So, the displayed diagram on your screen summarizes your accomplishments and also shows where the data of each table resides. In this task, you will use Hive to run SQL-like queries on the data that now exists in the join underscore impressions table. This will allow you to analyze which impressions led to ad clicks. So, to instruct the Hive SQL client to print names of the columns as headers in result set, run the following command. It's set hive.cli.print.header equals to true. To return the first 10 rows of the data in the joined underscore impressions table, run the following select command. The results should return quickly. What you see in the video captures the first few columns for the 10 rows that are returned in the results. So this proves that the table has data. Now let's run a more interesting query with this select added function. This query will return the added or add ID values for the 20 most clicked ads during the hour of weblogs that we have been analyzing. And while the result will be interesting, it might be more interesting for us to figure out which referrers to the website provided the users who clicked the highest number of ads. Referrers are the websites that sent visitors to the website that you are analyzing. So to exit Hive CLI, run the following command, exit. Even though we have exited from the Hive CLI, we can still run command against our dataset. So copy the Hive space -e space select referrer code in your GitHub and paste it in this bash terminal. It won't be visible here, but if you have successfully pasted that command, you will be able to see the same configuration or the same output being displayed on your screen. This query will return a list of the top 10 most effective website referrers, meaning that the referrals resulted in the most ad clicks. Of course, if you use the code that was found in your GitHub, where the Hive space -e select referrer code, you know that the result will be written to a file. So we see that here it took around 37 seconds. As the previous command completes, we need to run the following code. cat space /hadoop/result.txt to read the result of that query. And there we see that the top website referral is 49 from ibibo.com. To exit the SSH session, we just type exit. And to analyze one of the log files that make up the output of Amazon S3, we type in the same command as we've done earlier. Next, to download the file that contains the data that you have been querying, get the command code from the GitHub file, replacing the bucket name, and run the code. A new example-log.txt file appears in the file list of the environment window on the left side of the IDE. Recall that when you created join underscore impressions table, you specified that the data should be stored in sequence format. Now, this isn't a normal text file, but Hadoop can interpret it. That is why some of the contents of this file doesn't display well in the text editor. So it will take a while to open this, but when it does open, a lot of it might not make sense from the text editor standpoint. So congratulations! In this lab, you created an EMR cluster and then you used Hive to create a data warehouse based on two sets of log files that you merge into a joined table. You were then able to run queries to uncover some trends in the data, such as which referrals to the website resulted in the most frequent occurrences of users clicking the ads. Before we end the lab session, ensure to delete all the resources that incur costs for you to save up money. So in this particular case, we need to terminate the cluster from the Amazon EMR by going to the Hive EMR cluster management and choosing terminate. So in this recording, I've already started to terminate it. Next, prior to deleting the CloudFormation template, we need to first delete our VPC, the lab VPC, as it won't be deleted automatically by the deletion of the CloudFormation template. So we'll delete this. After that, we can now delete or terminate our Cloud9 environment first. We can do that by deleting the EMR Lab CloudFormation template, as our Cloud9 has been created through that template. This is one of the advantages of the CloudFormation template that we have discussed during the first lab session. Now, when we do delete this CloudFormation template, the resources that it created will subsequently be deleted as well. Notice that the two templates, even the Cloud9 above it, is automatically being deleted. Wait for it, and then after a while, once you have confirmed this deletion, we have successfully cleaned up our resources here. And with that, we end our lab. Hopefully by the end of this lab, you were able to see how using Amazon EMR can help you gain insights and handle your large data such as logs in order for you to leverage them for your decision making. Thank you for watching, and hopefully see you in the next lab.